to the Bangalore Theory Seminar. Today our speaker is Sayantan Sen. So he is a PhD student from IISc Calcutta and he working under Saurabh Chakraborty. Prior to that, he was at the CMI, and prior to that, he did his bachelor's from Jadavpur. His interests are in general randomized algorithms, and he's currently doing property testing. So what do you? Sorry. Yeah. Over to you.
Yeah. Oh. Thanks for coming. And also thanks to Anand and Siddharth for hosting me. So this will be a talk in distribution testing. So I'll formally define every notions that are required. So this is a joint work with Saurabh, Eldar, Arijit, and so this will be more or less the structure of the talk. So I'll introduce the problems that we'll be studying, and then we'll explore what our results are, and then at the end we'll briefly discuss the techniques. So, and at any point, if you have any doubt, please just ask. Okay, so let's start. So here there's no point of this slide, but my point is we are working on discrete distributions here. So we're not working in continuous domain. So like it's typically you are assuming it is from 1 to n. Okay. So once we have this, so we can define what is called a distribution. So a distribution property is nothing but a collection of distributions which are defined over the same domain n. Okay. Now, once we have these distribution properties, so we can characterize various distribution properties. So one of the distribution properties that we'll be focusing in this talk is the label-invariant distribution properties. So roughly, so given a distribution B, you can think it as a multiset of its elements, right? So if its probability of say element 1 is say 2 by n, in this multiset, I'll keep 2 copies of 1 and so on and so on. So a distribution property is label invariant if this multiset actually determines whether a distribution is in the property. So intuitively, the labels of these underlying elements doesn't matter. So this is like formally captured. So with this definition, so you apply any permutation and obtain this distribution that is also in the
property. So you're assuming both in the previous slide and here that n is
known. N is known, of course, n is known. And we'll see something what happens when they support. So initially, we are assuming that the distribution is supported over 1 to n, but at one result, we'll assume what happens when you do not know n. Can we do something about it?
So in particular, mean of a distribution is not labeling.
Sorry?
The mean of a distribution.
Yeah.
Not
yeah. So, sorry.
If I look at the, so if I compute the mean of the distribution, the expected value under the distribution, that's not labeling.
No, yeah. So typically, yeah. So yeah. So I think yeah. So actually, once we have this definition, so actually there are several properties that are actually label invariant, and that is kind of a rich class. That my point is. So there is this uniformity property. So we have a distribution T, and we test whether it is uniform or not, right? Or similarly, whether the support size of a distribution is at most n or it's like smaller than that, or whether this like entropy is at most. So I'm assuming it's random entropy. Okay. So label invariant properties are kind of like several common properties are actually label invariant. But also there are properties which are not label invariant. For example, the monotonicity property, right? So suppose we are assuming, say, a distribution which is not uniform, and suppose we are assuming that monotonically decreasing. So if you have apply a permutation, a small probability mass element can appear in the first place, and that doesn't remain like monotonic, right? So once we have all these properties, so there are also properties which are label invariant. Also, it works both ways, right? So our natural question is how we are going to get this. How are we going to access these distributions, right? Now, in this talk, I will assume a very simplistic model. So we are assuming that the distribution is over is given as an oracle. So there is some sort of a red button, and if we push this button, the oracle gives us a sample. And these samples are coming based upon this underlying probability. And we are assuming this all these samples are IIDs. So we have a distribution, it is stored as an oracle, and we are getting some samples, and we want to argue whether this underlying distribution has some property. Okay. And the complexity measure is like we want to minimize the number of samples that we require to determine whether this distribution. Okay. Now, once we have this, so let's define what we mean by exactly properties. So here, suppose we have a property P, so it's nothing but a collection of distributions. So the idea is to design a randomized algorithm A such that we are allowed to get IID samples from this distribution D, and we want to distinguish whether this distribution D is close to this property or it is far from this property. And of course, with high probability, complete randomization, right? So this is the formal notion of property testing, and that we'll study this. Okay. Now, once I have discussed this notion of closeness and farness, so what is the exact distance measure? So here we'll be talking in L1 distance. So a distribution D is close to a property P if the minimum distance from all the distributions in the property is at say epsilon. Okay. So similarly, we can define the epsilon to far property, right? Now, let's go back and see if we put 0 over epsilon, then the question becomes, is D is in the property or D is far from the property? It's kind of a 0 versus epsilon gap, and this is kind of epsilon 1 versus epsilon. Now this epsilon 1 equal to 0, where we are kind of distinguishing whether this distribution has exactly the property or it is far from this property, we call it as a non-tolerant testing, and the tester A we call non-tolerant tester. And when this epsilon 1 is non-zero, we call it tolerant test. Yeah. Sorry. No, it will not be far. So, so here, suppose I'm putting epsilon equal to 0, and I'm keeping epsilon 2 as it is. So, so the algorithm that in that scenario we want to design, its goal is to say yes when D has this property, or it is far from property. So it's kind of a 0 versus epsilon gap. This is we call non-tolerant test.
Yeah. So it does not matter if the between the field.
Exactly. Yeah, that's a great question. So here we are actually do not care whether this distance is between epsilon and epsilon. So we are off the hook. We can say yes or no in between this gap epsilon epsilon, and this gap is actually what gives us power. I mean, we can particularly decide whether a distribution D has a particular property or not. That might be hard, but we are actually working on a relaxed version problem, and that is where we are gaining dependence. Okay, so when epsilon, just to reiterate, so when epsilon is equal to 0, we have non-tolerant testing, and when epsilon is non-zero, we have tolerant testing.
Okay, a quick question. So, for non-tolerant testing, as you defined it,
yeah.
Let's just take the simple example of uniformity.
Yeah.
So I could give you a distribution that's arbitrarily close to a uniform distribution.
Yeah.
And then you would need like infinitely many samples. Or
No. So suppose we give a, so suppose suppose our property P is like uniform. Okay. And say we are deciding versus 0 versus epsilon. Now suppose your distance is actually very close to 0, say very small.
you leverage epsilon to sort of.
Yeah. So suppose my point is, suppose we are designing a non-tolerant tester. So you are designing a tester which distinguishes between 0 versus epsilon. But suppose you are giving it an input which is not exactly 0, but is very close to 0. But
all you have to tell me is it's epsilon close.
Yeah, that is this close versus far is tolerant. So my point is, suppose it is we are testing for exactly 0. You are giving it an input which is very close to 0, but not exactly 0. Okay, then so there is a leeway. I mean, any non-tolerant tester is somewhat tolerant because it is extremely close. We can say it is kind of okay to say, because this in between gray area is where we benefit. So in a sense, I mean, every non-tolerant tester has some sort of a tolerant property, but it's not for arbitrary epsilon on epsilon. Although it is somewhat tolerant, but it's not exactly tolerant.
The case where only probability for one of the element in the domain is actually moving the epsilon to 5 property.
Yeah.
What can you do in that case? I mean,
So you are saying, so there is a particular element in the support which has a very large, and that is kind of offshooting.
Yeah.
So the idea is, suppose you have an element, say 1 to n, and suppose you have an element whose probability mass is very far and like putting far.
Yeah.
So its probability mass is very large, you know. So if we take samples with high probability, we'll be getting that element, right? So if we get a substantial number of that particular single element, we can actually infer that, see, this not. Okay, great. So it's kind of clear that tolerant testing is actually harder than their non-tolerant counterparts. Okay.
When you say harder, you mean if you give me a non-tolerant tester that's tolerant for a reasonable value.
No, so so our goal is to design testers which works for arbitrary epsilon. So in this algorithm, you are actually given these parameters epsilon and epsilon. So your algorithm would somehow depend upon this epsilon, and of course your sample complexity will also depend upon this. But in between epsilon and epsilon, say epsilon plus epsilon by 2 or something, I mean, we can do either way.
you will take these two parameters to be constant. I mean,
Yeah. So we are just taking some constant, but ideally you actually want to do it for him. So it must be less than 1, and like epsilon is less than epsilon. So non-tolerant testing is somewhat harder than non-tolerant counter, right? Now the natural question is, so suppose we have a non-tolerant tester of a problem. Can we somehow design a tolerant tester from that knowledge? Is there a general enough recipe that gets us to this? So suppose your non-tolerant sample complexity is Q, can we design a tolerant tester for that property, which is the function of this? So there's no known technique for this. So there is no general enough recipe that you give me a non-tolerant tester, I'll design a tolerant. So in this word, we actually kind of make a progress in that. Okay, so I just moved part. So this is the first problem that we'll study. So given a non-tolerant tester, can you design a tolerant tester for it? Okay. Now see, if you have a distribution, if you can somehow learn that distribution, so I formally define what we mean by learn. But suppose intuitively, suppose we know the distribution. So once we know the distribution, we do not need to perform any further samples. We do not need any samples, right? Then we can just brute force whether that is in the property or close to property, right? So this is some sort of known as testing via learn. So we learn the distribution and then test. So formally, what do we mean by learning? So given a distribution D, we want to output a constructor distribution D tilde, which is closed in L1 distance. So once, suppose we somehow do this, so we can test. I mean, we can do non-tolerant test, tolerant test, because we don't need any samples, right? Again, like in the whole talk, our goal is to minimize the sample complexity. So it turns out that it's kind of folklore result. So given a distribution D over N, you need order N square, N by epsilon square samples to learn a distribution. So if we want to test a property and the distribution is say from N, using this N by epsilon square samples, we are surely able to do that, right? The question is, can we do something better? Also, see, as Siddharth also told, so we know this distribution D is supported over say 120, right? What happens, we do not know it's. So suppose the distribution is supported over N, but its effective support is very small. I mean, well, by effective support, I mean all the support elements which has non-zero probability. So can we, in that case, beat this N by epsilon square? And of course, we do not know the unknown effective support set. right? So can we in that case give some bound?
Also, there should be a matching lower bound.
Yeah, this is tight. Yeah, this is tight. I mean, I'm just thinking in terms of upper bound, but this is tight. Yeah, this is tight. So again, can we learn a distribution? So this is the second problem. Can we somehow learn a distribution when support is on? Okay. So
Also,
yeah.
like this is too heavy a hammer, right? Like if you apply this theorem, label invariance is like you could tell any property.
Yeah, if you just learn, so this learning doesn't assume any property, right?
Yeah.
Once you learn a distribution, you can do anything, whatever you want, right? I mean, but if we take some more assumption on my class, can we do some better, right? Yeah. So this is the second problem that we'll start. Okay. So I'll just move on to our results. So if there is any questions. Yeah, sure. Yeah. No, I can tell you in board. I think I don't. I can tell you, but it's
that after.
yeah. So sure. I mean, I can do. So it's kind of very straightforward. Okay, so I'll
We just draw these many samples and look at the empirical distribution.
exactly, and like
That's
yeah. So okay. That is kind of enough. So okay. Sorry.
good.
Yeah, sure. So I'll just first describe our results and then we'll go to give a brief overview of our techniques. Okay. So in the first result, we show that suppose our distribution property is not general, but suppose it is label invariant. In that case, suppose a property can be non-tolerantly tested using Q samples. Then I can design a tolerant tester for that property with Q square samples. So there is a quadratic gap. Of course, I'm saying like I'm cheating a bit because there is a log Q factor, polylog Q factor, but here I'll not add it. So technically I should write O tilde, so hiding the polylog factor. But for the simplicity, I mean, it's not exactly Q square, but it's Q square polylog. So given any distribution property, which happens to be label invariant, once we know that it has a non-tolerant tester with sample complexity Q, we can design a tolerant tester with sample complexity Q square.
This independent of epsilon 1.
Yeah, this no, it's not independent of epsilon 2 because in tolerant there is epsilon 2, right? So we are a kind of hiding because they are actually constants. So yeah, actually depends upon epsilon 2 minus epsilon square. We're kind of hiding polylog and dependencies on epsilon.
But epsilon 2 is same for
Epsilon 2 is of course. But I'm kind of hiding because they are constant, so they doesn't in asymptotic.
So you say it's one by epsilon 2 minus.
Yeah, 1 by epsilon, of course. So it's surprisingly, our tolerant tester doesn't need to know what the non-tolerant tester is. So we can actually take it as a black box. In fact, we do not even call this non-tolerant tester. We just need to know a bound on this. And that is enough for the design of tolerant tester. Just a bound on is non-tolerant, sample complexity is sufficient. And this somewhat gives us a general recipe, right? Although I must say that this is not in general, but for a label invariant property class, which is kind of a rich class of properties, right? So this is the first technique this is the first result that we'll be discussing later. I'll give a brief proof, of course. Now the question is this quadratic gap tight? Can we design somehow that Q to the power 3 by 2? Right? Is it possible? It turns out that it is not. So consider a uniformity property. So what is the non-tolerant variant of this uniformity property? So you have a distribution and you can access the distribution using like samples, IIT samples, and you want to decide whether this distribution is uniform or far from. This is a non-tolerant variant and it can be done in order square root. Actually it's tight, but I'm considering So its non-tolerant sample complexity is square root n, and its tolerant is also n by 1. So there is a quadratic gap, ignoring of course polylog factors. So this quadratic gap as a whole for label invariant class is kind of tight. So there is a property, uniformity property, which actually has a quadratic gap. So in general, without taking any more other assumptions, we cannot hope to beat quadratic.
Does it hold for entropy also and the second thing which you mentioned?
No, entropy has slightly higher tolerance.
Okay.
But yeah, so my point is there is a property which has quadratic. So we cannot hope to generalize unless we assume more about properties. Yeah.
Actually gives me a lower bound, right? If I have a lower bound for non-tolerant, for tolerant,
Yeah.
that implies like a square root of that is a lower bound for.
Yeah. So this is kind of the first result that we'll be talking about. So now move on to, so just to move on to the second part. So we will also prove some sort of a result of lower bound result. So here previously we were showing that this for all label invariant properties. Suppose we assume something more about this distribution property. So can we prove some lower bound? So for that we need actually two definitions. So a distribution is called non-concentrated if its probability mass is sufficiently spread. So if you take a large enough support set, its mass must use at least some alpha. Okay. And of course, property is non-concentrated if only non-concentrated distributions. And similarly, we have this other counterpart, this concept, right? Now we show that non-tolerant testing of non-concentrated properties takes actually square root n. Okay.
Can you please say what normal?
Yeah. So non-concentrated is, so it is not particularly concentrated at a subset of its masses. So the probability mass of this distribution is some sort of well spread across it. So if you take a large enough support set, a large enough subset of its support, probability mass should be at least some threshold. Say, if its mass is the size of this subset is at least beta n, probability mass. So we actually prove that non-tolerant testing of non-concentrated properties actually takes square root. Okay. So here note that we are not assuming any label invariant. So this is for any kind of distribution problem. And we'll go over this. So this is kind of a generalization of lower bound of uniformity property, which takes square root.
You define non-concentrated distribution. What is non-concentrated?
So non-concentrated property is a property, I mean, only non-concentrated distributions satisfy.
So does this lower bound hold for uniformity as well?
Yeah.
I mean, the non-concentrated way.
Yeah, because uniformity is like the maximum non-concentrated, right? It's supported over whole 1 by kind of the maximum non-concentrated. I mean, yeah. The notion of maximum may not be right, but yeah. So this is a lower bound for non-tolerant testing. So what can we say about tolerant? Okay. So for tolerant testing, we cannot prove it for general properties, but we show that for label invariant non-concentrated properties, we need almost n. Okay. And in this proof, actually, this label invariant notion is necessary. Okay. And this kind of has a proof from the result of low frequency blinding. But yeah, so my idea is like label invariant non-concentrated properties is also hard for tolerant testing. But yeah, we are assuming a certain mode structure of this distribution. Okay. So this is like the brief result that we'll be talking, and then I'll just move on to the brief overview. I think this. So maybe move on. Yeah, so again, just to reiterate, so we have a property which is label invariant, and it can be non-tolerant tested with Q samples. So we are saying that it can be tolerantly tested with Q samples. Okay. So what is the rough idea? So we are kind of trying to estimate the probability masses of all high. So if the probability mass of an element is high, if we take sufficiently enough samples, so we'll hit those elements, right? And if we can hit those elements, we can again take samples and estimate their probabilities, right? So by here, what do we mean by high? High elements means all the elements in the support whose probability mass is at least 1/Q². So we want to correctly estimate all such elements, probability mass of all such elements. So like we can briefly say about its two phase. So in the sampling phase, we actually take as first a multi-set of Q² samples, and then we take another set of samples to estimate the probability. So here the idea of the first set of sample is we kind of want to know what are my high mass elements. So if we take, since high elements is 1/Q², probabilities are. So if you take Q² log Q, then with high probability we'll be getting a set of samples which contains all of these high mass elements, right? Then once we know what are potential high mass elements, so some elements can come here which are not high mass elements, but certainly with high probability, all high mass elements will be inside this. Once we have this set W, our potential candidates for high mass elements, we take another set of samples to kind of measure their probabilities.
Up to some.
Of course. And that's all. So we're not taking any more.
Why do you need to take another set of samples?
Yeah, that's a great question. So yeah, so suppose we had taken a single set of samples, right? In that case, if we apply, so we'll be applying union bound over there. So if we apply union bound, then we need a log n factor. But if you take two sets of samples, you need log Q. So we're kind of hiding that log. So this Q² has only poly-log Q. So things log square. We are not. This Q² doesn't have n.
Second set is just to avoid the union bound instances.
Yeah.
Over, you only want to apply it over the high mass.
Yeah.
You have a guarantee that there will be at most Q² of them.
Yeah.
Given that.
So if we are taking only one set of large set of samples, log n. Okay. So these are the two set of samples. So of course, sample complexity is 40 Q², and I'm hiding poly-log Q and its elements. Now in the second phase, in the testing phase, so see at this step, at this situation, I have all the correctly estimated with some error, of course, all the high mass elements. Now I will construct a new distribution detail. So how will construct a distribution detail? I'll put all the high mass elements. So I know all the high mass elements and their estimated probabilities. So these constitute a particular set of part of my support, right? But there are other elements which are not high mass. So whatever the remaining mass other than the high mass elements, we just distribute it as uniform for all the other. This gives me a distribution detail. Now, once I have this distribution detailed, it's kind of a learning, right? We know the distribution and we do not need to perform any other samples, right? But once I have this distribution detailed with me and I know this distribution property, right? So distribution property is nothing but a collection of distributions. So we know those distributions is my property. So I can check whether this distribution is like close to detailed and these high mass elements are inside. So we need to ensure that all high mass elements are also properly estimated. Because the first set of samples may have some elements which are not high mass elements, right? If you take a set of samples, some low mass elements can come, right? It's a randomized procedure. But we are guaranteeing that with high probability, all high masses elements will be there, right? And that's it. So we have two phases, sampling phase and testing phase. So from sampling phase, we get a distribution d tilde. And once we have this distribution d tilde, I can do this test. And that's all. My claim is this is my distribution. This is my tolerance. And it has sample complexity already used. Right? Now, so of course, why does our tester repeat? Right? So again, the idea is we are kind of correctly estimating 1 over high mass, 1 over elements whose probability mass is 1 over 2. And that is good enough for us. Because all the other elements I am kind of distributing as a uniform, right? So again, just to reiterate, we just need to know this bound about how many samples we need to take. We are not even calling this non-tolerant test as a black box, or we do not need to know how it works, right? And yeah. Now recall, so this is our. Now I just want to point out a particular place. See here in the test second part of testing phase, once we have this distribution detailed, we are actually testing whether there is a distribution in my property which has these two properties. Now see, this distribution property is a collection of distribution that is given to us. Potentially, this distribution property can contain a huge number of distributions, right? Theoretically, it's possible. So checking this kind of a brute force way can take a large time, right? So can we actually do a more time sensitive thing, right? So although our prime focus is only minimizing sample complexity, but can we actually do little saving on time, right? So it turns out that for linear properties, we can do it in polynomial. So what is the statement? So suppose we have a property which is label invariant, and the property can be expressed as a linear, like a feasible solution to a linear inequalities with at most m. Then our tester takes the same number of samples as before and runs in polynomial time. So basically, in the second phase of our tester, we actually transform it into a linear inequality form, and then we apply a normal techniques for programs.
Questions. What is a linear property?
So it is a property. So suppose we are considering the uniformity, right? So we can write it as a linear program, right? So all the mass elements are 1 by n, and they sum up to 1, and then. So basically, what happens is we actually transform it as a convex set, and then we actually test whether there is a non-negative solution.
Vectors of probability, like is a convex set in the
Yeah.
simplex.
Yeah, yeah, exactly. And then we apply a. So for linear properties, we actually have a tester which runs in polynomial time and with the same numbers.
Questions that probably a bit late. But we give you an example of property where q square is like significantly less than n.
Yeah. Yes, so in general, yeah. Suppose we have, suppose we consider this property. So whether this support is at most k. So it takes k by log k samples. But if we apply that, then you have a significance. But for where this is already the non-tolerant testing is some sort of square root n.
Yeah.
So quadratic doesn't give you any extra benefit, right? I mean, but for that kind of property, we can actually.
K less than square root n
Yeah,
or something.
yeah. And then support size at most k kind of gives us.
One more question. It got to be presented. So where are you using that n? Firstly, you are estimating the high mass elements. Seems like you need n. After that, you are just
No, so the idea is like, yeah. So as Siddharth pointed out, so suppose q square is more than square root n. So in that case, we will not apply this tester at all, right? We just learn. Say suppose q is say to the power half plus some epsilon, right? Then q square would be overshooting n.
So initially you said that the value of n needs to be known for the algorithms are called.
No, this algorithm doesn't, but the learning thing. Oh, right. Yeah. So yeah, thanks. So because in detailed, thanks. So in detailed, we are actually distributing all the remaining masses. So in construction of detailed, we're actually putting all the high mass elements.
So first, have you identified the high mass elements?
First, we have identified the high mass elements. Then we estimate their high mass elements.
So by estimating, you mean you're just going to count how many times they appear?
Yeah. So yeah, divided by the
total.
total.
Already be putting all the mass on the masses.
No, we'll be like averaging it out. So suppose suppose I have taken a high mass, so I, suppose element I. So I'll see how many times I has appeared in Z by size of Z. So this step will somehow give us a good estimate on the high mass elements. But they may not contribute to all probability mass 1, right? So what are the for the remaining mass? I'll just distribute them uniformly over all other mass. Yeah, thanks.
C minus W would be non-empty. That's the remaining mass you'll spread out there.
No, the some elements may not even appear in the samples, right?
No, I'm saying, Hans' question was what is left out.
Yeah, what do you
So it's like there will be some non-high mass elements
That also appear in W.
yeah, which will give you some residual probability to spread across.
Yeah. But again, like our case, just if we kind of estimate the high masses, we are good enough. Yeah, thanks.
Even D1, it would require you to know.
Sorry.
Yeah. Even D1.
Yeah.
Like finding the D1, it's these subsequent properties might require you to know N.
Yeah. Because I need to know detailed on this, and then I have to check whether there is a distribution which is close. So I take a distribution D1 in my property and test whether this is close to. And here we are not considering time complexity, so we are. For linear properties, we can polylinear. Now, yeah, so I'll just now go to the second learning result. So
You can do this just because the two properties you want can be expressed as linearity.
exactly. Yeah.
Even distance.
Because, but for like I'll say at the end, but for like, so there are properties which are cannot be expressed as linear equality, say entropy. Then it's not very clear how to.
For entropy, it's not obvious, or like there's no other method known that does a similar thing.
For entropy, like similar thing means in with respect to time or like.
Yeah, I guess I mean you don't. So again, probably for entropy, the question becomes: is there a distribution D1 with high enough for this
Low
much
enough. Yeah.
entropy such that it's L1 close to B tilde?
Yeah.
And it's not known whether that can be done for it.
No, so at least our technique doesn't work, and we don't. Because it cannot be expressed as linear inequality, but convex inequalities things might get tricky because to apply ellipsoid, you need to cover the thing with a inside wall and outside wall. Then things can get tricky. At least, I mean, we can apply some high technique, but I don't know. So the second properties, so we need something called concentrated. So I defined it before just to reiterate. So a concentrated distribution is, so there is a set, but it's very high in mass. Its mass is very close to 1. So suppose D is such a distribution, and suppose we do not know S, right? Then we say that O tilde S samples are enough to learn this distribution. And this happens when like we do not know S, right? And we also, our tester also works when even we do not know the size of S. So unlike the n by epsilon square result of learning a distribution, we know n, right? We know the support and its value. But our like learning algorithm doesn't. So I'll just give a brief overview. So before going to the overview, I'll apply a result for our learning algorithm. So this is a result by Valiant and Valiant. So suppose we have a known distribution dk and unknown distribution d. And suppose they are over S elements. I know S. Then we can distinguish whether they are close or far in L1 distance with S by log S. Okay. Now, once we have this learning result over a known S, we actually do a doubling tree. So we basically start with S equal to 1. So we take a O tilde S many samples, and based upon that sample, we define a critical distribution and we test. So our D is unknown, but our DS has become known. Now we apply this Valiant and Valiant's result, and if they are close, we are good, and output DS. And if they are no, then we actually double and keep going, right? And it may so happen that like it overshoots, right? It's like just very small to M, and it has gone like to M. Then we report it, and we prove that this case doesn't happen with very high probability. So we are good with this. Okay, so we basically apply a learned doubling trick, but our technique actually works when S is unknown as well as the size of S. Right? And this actually takes only O tilde S samples. Right? So this is other than the n by epsilon square general learning. Right? So this is our learning. Is it okay? I mean, and then, yeah, I'll just briefly go over this lower bound technique. So for lower bound, we have actually said that we will prove that non-tolerant testing of non-concentrate properties takes square root n samples. So we'll just take a slightly simpler problem first. We first prove that this lower bound actually holds for label-invariant non-concentrate. So again, label-invariant is the labels doesn't matter. The multi-set actually defines whether this distribution is the property or not. And non-concentrate means the probability mass is sufficient. Right? So the idea is as follows. Suppose we take this distribution from the property. Now we'll construct. So I'll prove this by IISc technique. So I need another hard distribution D. So I'll construct my distribution dno from messaging this. So how I'll do that? So suppose we know the support is n, right? And I know ds. So I can actually create these two sets L and H. L contains the smallest two n elements of n depending upon ds. So we know all the probability masses of ds elements. So we can actually take the smallest two beta n elements. So here beta actually we are considering of alpha beta. So if we take a beta n size set, this probability mass would be at least 1. So it is this beta. Okay. So once we have this DES, we can characterize this support set into two sets, the smallest two beta n and the. But these two beta n elements will actually partition into two parts and make their pairs. So we have actually partitioned into beta n pairs, call this partition P. So this, all these things that we are doing is to just construct this distribution from where we can apply this EOS. So we have actually get this PL, which is a partition of elements. Now I'll construct my, but we wanted to do this construction hard distribution dno. So if a particular element Z is not in L, we are actually keeping it as it is. And if it is in L, we are actually pushing all the probability masses to a particular element in the pair. So now dno has support at most 1 minus beta, right? So I put beta, so effective support at most 1 minus beta because I have put at least beta and entries, right? Now these are my hard distribution DES and these two distributions, they are same on high mass elements and kind of I have broken. These two distribution only differ in this low mass, right? If we take enough samples, unless we hit two low mass elements, we cannot distinguish them, right? So this is our case. These two hard distribution DES and dno, we need at least square root n samples to distinguish whether this is. So given any tester, suppose with probability half we give it DS and with probability half we give it dno. The tester needs at least square root n samples to distinguish whether it is DS or D. Okay. So we actually show that for all low mass elements, that probability mass is over 1 by. This actually follows from this property of non-concentrated. Now, once we have this result that all the probability mass of all elements in low is 1 over n, and since DS and dno are same over high mass elements, right? Unless we hit two samples from low mass elements, we cannot distinguish, right? So by Barde paradox, we need square root, right? This is very much reminiscent to the idea of uniformity testing. So the idea is like, so suppose we have taken a uniform distribution, which is 1 over n. And from that, we actually take only this odd elements to be 0 and even elements to be 2 by. So I can only distinguish if we can hit these two elements in the same scenario. And by Barde paradox, it's square. So this is more or less the same, right? So this gives us a square root n. Now note, our initial goal was to prove a general lower bound for non-concentric. We took a little detour and proved a slightly simpler version with more structure. But can we say something about leveling? Non-leveling, right? So it turns out that same complexity is required, but previous technique doesn't work because we are actually moving these elements, and for this thing, we actually to prove this lower bound, we have to actually apply a random permutation, right? Whatever these distributions that we are appearing, we'll apply a random permutation over this, right? Otherwise, we cannot hide them. Uniformly random. If the property is level invariant, if we apply any permutation, the distribution will remain in the property. So we are good here. For non-level invariant properties, once we apply this permutation, the distribution that we get may not be in the property, right? I mean, that doesn't work, right? So how can we bypass this? So we actually do kind of weighted kind of technique. So as before, we keep the same mass over high mass elements. But instead, previously I was just fixing the elements. But here with this probability, it's kind of a weighted average. We are moving these elements, moving the probability masses over this. Now, DS and dno only differs over low elements, and we can distinguish DS and dno if we can get two samples from the same, right? That happens. Of course, yeah, the probability mass is of course 1 in 5. Again, by Barde paradox, we can actually say that it takes square root. This is 1 word.
I see something in theorem statement. So imagine that I'm looking at like the mean of distribution. So that's a non-label invariant property. If I change the label, the mean changes. And I can look at it for non-concentrated distributions as well. But estimating means does require like only logarithmic in it by concentration, like putting or something. So what am I missing? Example.
No, so sorry. So you are kind of testing whether the mean of a distribution is
Is less than some threshold tau. It's a I agree, it's a non-label invariant property, but I can look at this property.
Yeah.
Here's my property. Is the mean less than n by 2?
Yeah.
Right.
no, that is okay.
It's non-label invariant. And I can define it for non-concentrated distributions. Look at it for uniform distributions or. But then it's actually like the sample complexity is not good. Putting or something will tell me to do that. Log in. So is that not a
it can be done login.
minus u square?
Mu by mu epsilon square.
Yeah. So it's the additive error.
Yeah, I think that is what, right?
It's not
One
one.
here also show there is one hard distribution.
Yeah, of course, that is
Okay, so this theorem statement is there exists non-tolerant test. There exists
Oh, right, of course. Yeah,
It's
yeah.
not for all.
No. Sorry, of course. Yeah, sorry. Yeah, I
The
probably.
way it was written was sample complexity for.
No, actually, yeah. So
There exists a non-concentrated property.
So we cannot generally design a general enough tester with this.
Got it.
Yeah. Sorry. Yeah. Actually, thanks.
So can you define what L was again?
Yeah. So L is the smallest 2 beta n elements. So we have this distribution ds from my property, and based upon ds, I know the ds, right? All the elements of this. I take the smallest 2 beta elements. So beta is less than half. So and we just only want to massage L, right? Same as A. So it even works. Suppose there is a. So suppose you can, if the tester knows beforehand what is the probability mass of high mass elements, suppose you give them as free. Even then, to distinguish, since these two distributions are only differing in low mass elements, even if you know the full knowledge of high masses, still square root n.
I can take back my point. I could define the property as the mean less than n. Of course, I need 0 samples. Every distribution has mean less than n. Define here.
Yeah, that's true.
0 samples.
Yeah, so also this takes square root n. And I'm not discussing, I mean, the label like tolerant thing, because that directly follows from our. Just have to introduce some more notations that I want to put under the gun, but this kind of a direct applications. But I just want to point out that this non-tolerant sample complex, we first showed it for non-label invariant, for label invariant, then we do it for. But for tolerant, it can only show for label. It is due to this result that we are applying. This notion of label invariant is very required. So what they do is they basically take a set of samples and consider the histogram of these samples. How many times one has appeared. And then they analyze this histogram. But for non-label invariant, the technique doesn't directly work. So I'll just conclude. So, of course, first question is we need non-label invariant counterparts. So our quadratic gap tester works for only for label invariant, right? But can we design such a tester for non-label invariant? Also, like as Siddharth pointed out, so we have a constructive tolerant tester which runs in polynomial time for linear properties. But of course, there are properties like entropy, which is convex, and it's not clear to us. Can we design a tolerant tester which has good time complexity? So that's also another question that see, and also we see that for this label invariant non-constrained properties, we prove that it is n to the power 1 minus 2 log. But can we actually improve to n by log n? They are more or less the same, but significantly better. So these are kind of problems that not no answer, but eagerly wait. Thanks. Bye.
In the second question, you mean efficient?
Efficient, like in polynomial time. So you have, so basically we construct a distribution t tilde and we test over all properties. But so for convex properties, if we apply ellipsoid kind of technique, so you need to cover it with two balls outside and inside, right? So the runtime depends upon this R by R kind of.
Very big log of R.
Yeah. But
the point is that maybe you don't even need to find exactly D1, but you can even relax the property to something more and like find a D1 that's epsilon 1 by 2 close to the property and has this. So
but
might
again,
be able to leverage that.
in this testing, this whether a distribution is in my property, which is close to this. So for this, we need to some sort of a black box kind of thing, which does not depend upon the mass of that set, right? And so my set, I'll represent it as a convex set, right? Volume of that convex set would be.
Yeah,
I'm not very much knowledgeable in this technique, but if you have any idea.
because like a lot of time it helps to like just have separating hyperplanes. So the idea would be you have these linear functions and their expected value under two distributions. It's almost like okay, there's a separating hyperplane for the property and so which would mean maybe in this context would imply that there are linear functions for which the expected value under the two. But yeah, this needs some thought.
Oh, okay, I see. So you're kind of creating a separate hyperplane that separates this distribution and this property, and somehow from that you can massage this epsilon distance and.
Yeah, so D1 could be like if you look at it from query optimization, it would be like the projection of D tilde on
the
supporting hyperplane.
right. Yeah.
But that's for just to be clear, that's for L2.
Yeah.
You want here total variation. So all of this are implications that one needs.
Yeah. So yeah.
Which again, like if you have square root n, you can't afford square root.
Yes. In our algorithm, yeah.
We're doubling.
Yeah.
Right. So why doubling this?
So it basically does like log.
Yes. So in the very beginning of your talk, you mentioned that all these
discrete distributions.
So which part of these fail if you can see?
So the idea is when you take continuous domain, how are you getting samples? That part is not very.
So by discrete, you mean that each sample will take the discrete values.
Right.
You can have some distribution which is from continuous domain and you can get samples in continuous domain.
But then how do you argue?
No, n can still be finite. Right? I'm saying n is finite, but the value.
Oh, okay.
I see. But
because is like, is it necessary that the support is integers 1 through n, or it could be any arbitrary n elements.
Would be the real line, 0 to 1.
Yes, yes.
Yeah, the support related to real line. It's not very clear. Like, how would you suppose you want to see take a set of samples and see how many times it will appear, right? How do you argue that?
So I guess what you could do is try to bucket it.
Yeah, yeah.
Yes. It comes in there, you count as.
Yeah, we can actually bucket it, say logarithmic number of buckets. So 2 to the power I kind of.
So I was thinking bucket of equal size. After said epsilon.
Oh, you are talking about buckets of equal size. So there will be like n by epsilon many buckets. Right?
I mean, it's a 0-1 interval, it will be like 1 over epsilon.
1 over epsilon. Yeah.
Ceiling.
Actually, it's not very well studied. So in this continuous domain, there might be some intricacies which more. There's certainly more intricacies. I unfortunately can't say.
So any of these theory fail or something?
I don't know. I don't know any particular example that it fails.
The bucketing can work well only if the distribution obeys some nice.
So we can always assume some extra properties and null property.
Yeah.
Always, I mean, say even for label-invariant, I mean, cannot prove it for general. So let's try some rich enough class. Of course, if you can prove non-label-invariant, it will be a kind of those are kind of thing. But right now, I do not think. Yeah. So one technique kind of bucketing actually. So as you mentioned for bucketing, so in uniformity, so uniformity takes square root in many samples, right? So there are several approaches to solve uniformity. So one approach is called bucketing. So kind of like bucketing into logarithmic matrices, 2 to the power I kind of. So bucket 2 to the power I, 2 to the power I plus 1 kind of all the elements. Then we actually see how many elements are inside a bucket and it's Herbover. But yeah, I think there are probably must be some intricacies for other intricacies that I can think of, right? Yeah, in general, continuous, as far as I know, has not. Next.
Results like Stockholm total variation to L1 to like Gaussian. Very Santosh is like there's literally like
Yeah, I saw. Yeah.
so like total variation to mixtures of Gaussians.
Okay.
It's like parameterizing the
Schema, right?
It's the continuous. Then you
So that's sort of the standard one.
Sorry,
So parametric families.
how are you parameterizing?
So pick your favorite French mathematics.
Oh, okay, I see.
Look at family.
Yeah, Poisson. Okay. So also this L1 distance, so there are some other works where we apply study other than variations.
like the PDF has two times. It fits that enough for this kind of.
Yeah. Yeah, I remember some works like that. So yeah, mixture of Gaussians. So I'm not very well conversant. Yeah, there's well conversant. Yeah, so besides this, I think there are some other distance here like say chi square or something. But L1 and L2 are kind of close because I can apply Cauchy Schwarz. Also another, so yeah, so just to like say for interest, so here we are only considering about samples, right? We have a distribution, there is an oracle, you get samples. Now suppose these samples that we are getting, they are very large. Suppose this distribution is supported over, say, high dimension, high Hamming cubes. Even if we get these samples, reading the sample size is super large, right? Here we are implicitly assuming that the oracle gives me a sample, I can read the sample in entirety, right? But if the size of the sample is super large, then reading that sample is kind of very costly business, right? There is a very recent model where they also ensure this complexity. So there is a sample complexity, and once you have this sample, this is basically a string, right? So how many queries do you need to perform to this string? So meaning the query would be give me the ith bit strings. This is kind of a called a huge object model. But recently we have also done some work in that model. So basically we showed that, so in general, these sampling techniques are all kind of non-adaptive, right? But when you perform queries, adaptiveness can make it, right? So we can define a particular class of properties where like gap between adaptive and non-adaptive is kind of time. So in practical sense, these things are quite important, right? If distributions are like coming from a high domain, and reading those samples, the single shot might not be very. Yes. So they also take this, but this is a very recent example. This is very recent work. The original work they study, so it's really study. Yeah, but that's a detail.
You can
Thanks for attending, and also Siddharth.